Okay, number 3 is asking us which electron transition produces light of the greatest frequency in the hydrogen atom. So I don't know what this IS here stands for. Is it, maybe I'll click this image to download and see if there's a better explanation for this. Just give me a second. 220. Oh, it's 21s. Okay, so it's not IS. Okay, that makes sense. So it's 2 back to the ground state. So I thought it was talking about LS. So this is actually a 1 here. So that makes sense. Okay. So let's click 3. So this is 3. So it says, I want the produces the light of the highest frequency. So highest frequency of light produced in the hydrogen atom. And then I'm given 4 options here. So A here is 5p21s, B here is 4p21s, C here is 3p21s, and finally D here is 2p21s here. So what is our highest, which one would be our highest highest frequency of light produced in the hydrogen atom, right? So let's look at this here first, and we're looking at basically our energy levels, and it's all basically it's all going to emit energy to go back to the ground state. So if I were to draw out kind of the energy level diagram for this, I'll draw it for only A because they're all very similar here. This is delta E here. So you can think of this here as this state here would be a 5p state, and this here would be the 1s state, which is our ground state. It's going to emit here some type of energy, right? Some type of energy here is going to be released for us to and then in this energy, while it's being released, it's going to have a specific frequency of light that's being produced, right? So this here is going to emit some type of frequency. So this here, I'm going to get some type of energy that's being released. So this works for the 4p, for 3p, and for 2p. It's asking us which is the highest frequency of light. So if I were to look at our equations here, what we kind of have to first find out is our relationship between the energy levels and how much energy it's going to be released. So let me bring you back and recall that we know that we have a couple of equations that we know. So we know here that E energy equals hc over lambda. That's a delta, sorry, over lambda here. Meaning that our energy equals our Planck's constant times our speed of light. Again, h here is our Planck's constant, c here is our speed of light, divided by our wavelength here. And we know that also, we know that because E here equals hc over lambda, we also know that our wavelength, or lambda, equals our speed of light divided by our frequency, right? So these two are things we know, right? These two are kind of equations that we learned either in physics or in chemistry as well, because actually we probably have to reorganize this. So we probably knew that V here equals F times lambda, and then therefore lambda equals V over F, right? So this here, lambda would equal, lambda would equal V over F here. So maybe it's something that you might learn from physics or something like that. V and C here are interchangeable. So let me for this problem specifically, so let me rearrange this. So we know that this is equation 1 and this here is equation 2. What we can do is actually sub 1 into 2 to find our relationship, right? So in order for me to do that, I'm going to have, say, E equals hc over c over f, right? Or you could rewrite this as hc times the reciprocal f over c, right? And again, the c's here cancel out here, so my energy here is simply just at h times f here. So this here is going to be my proportion. So energy equals Planck's constant times our frequency, and assuming that they're both traveling at the speed of light here. So this here is actually a really good proportion, and really good to what we need to know. And if I know that energy is equals Planck's constant times F, we know that in conclusion, energy is proportional to our frequency of light, right? So therefore energy here is proportional to our frequency of light that's being produced, which is really, really good, because then if I want to know the highest frequency of light, then I'm simply just figuring out the highest, what would give me the highest energy, because highest energy would equal our highest frequency here. So this, I want to know the highest energy released would produce my highest frequency of light. And according to these 4 options here, which one would be the highest energy that's being released? Well, obviously it would be the one that's furthest away from the ground state, which will be option A here. Because option A, remember, if you look at the electron configuration, this here would be much greater in terms of energy than 2p, right? If I were to write out the 1s state, again, 1s is all the way here, and then it's 2s, 1s2, 2s2, 2p6, 3s2, 3p6, and so on and so forth. And as you can see, the higher the number here, the higher the principal quantum number, because here n equals 5, this is n equals 4, n equals 3, and n equals 2. The higher the principal quantum number, the higher the energy that's being, the higher the energy level, and the greater amount the energy will be released. So therefore, it's going to have the highest frequency of light being produced here. So number 8, option A is correct, and they wrote here option A is correct as well, and they explained it as the energy of emitted light by the electron transition is again, these are not complete sentences, so it says here, it doesn't really, it says solution, the explanation is really bad. So I'm going to say solution is correct, analysis is incomplete. And I'm going to basically stay here. We know that E equals hc over lambda. And we know that our speed equals our frequency times lambda here. So therefore, E equals h times f. So we know that energy is proportional to frequency. Therefore, the higher the energy level, the higher the principal quantum number, the higher the energy level, and the higher the energy that is being released. Therefore, increasing the frequency of light that is being produced. So this here is actually the correct, this here would be the correct analysis for this problem. So I'm going to say solution here is correct, but they just had a very, very poor analysis because I think their question was probably cut off by something here. So I'm going to say solution here is correct.